Hello everyone, welcome to the ninth week of the interaction session for the control systems course. My name is Soumya and I'm a PMRF fellow at IIT Gandhinagar. Last week we did a few questions that were basically a recap of what we had done over the last few sessions. It was in general giving you a brief idea about all the concepts. Moreover, till now we know that we have studied about two concepts, namely the Routh-Hurwitz stability criteria and root locus that help us in determining the stability of the system. So I was telling you that we have a few more methods and we are really into it. So we have Bode plots, we have Nyquist stability criteria, we also have Nichols plot, then we'll see lead and lag compensator. So like this, the course will go on. So today it would be an introductory session of Bode plots. We'll start seeing how the graphs go, uh, how the magnitude and phase changes with change in frequency and all sort of things. So it would be a basic building block uh, interaction session. In the next session, we'll have a few more questions on Bode plots plus Nyquist stability criterion with MATLAB examples. Today, we'll see whatever has been taught in the Bode plots and proceed with the questions. That would help you in really solidifying the concepts. Okay. So I have some snippets from the notes itself that is already shared with you. So when we say Bode, just yeah. When we say Bode plot, why do we actually have Bode plot? So in root locus, with the help of open loop poles and zeros behavior, you try to determine what would be the behavior of closed loop poles, relating it to stability. That okay, if my root locus goes in the right of the S plane, or my poles, closed loop poles always remain in the right of the S plane for any value of k, then the system is unstable, right? In the Routh-Hurwitz also, you said that okay, if there is any sign change, that means the poles are going to lie in the right half of the S plane. Hence, my system is stable. Now, if there is a method, a simpler method, we can say, that help us determine what if we can find out the stability using some magnitude criterion, some phase criterion. So we'll see in the next class basically that how gain margin, phase margin, uh, gain crossover frequency, phase crossover frequency, all of these parameters in the frequency domain actually help in determining that if the system is stable or not stable. So for now, what we are going to do, we have a method called Bode plot. In Bode plot, we actually plot two things. One is the magnitude of the function that you're given, basically the closed loop transfer function, and for the phase plot. Okay, both of them, one would be magnitude with respect to omega, one would be angle with respect to omega. Omega is varied from 0 to some value. Uh, okay, so what we're going to do, okay, then we'll have the next time we'll have Nyquist plot also, where you'll have some plots between real value and imaginary value of the transfer function in the PS plane. So this would be an important factor. It would now no more be in the S plane, it would be in PS plane. So we'll see that. And Nichols plot is also one of the things that help us in determining the stability criterion. Okay. So let's say if you're given a transfer function which has magnitude and phase, both are functions of omega, right? Because everything can S can be replaced by j omega always. So when you try to find out the magnitude, you would just take the magnitude like under root of real square plus imaginary square. But we have a convention of representing the magnitude in logarithmic scale, and we convert the magnitude in dB. Now, why would anyone go to logarithmic scale instead of linear scale? Was linear scale was doing fine, right? You had on this x-axis, you had 1, 2, 3, 4, and everything worked well. Why would anyone go for logarithmic scale? The reasons being, so this is a linear scale, right? Omega 2 minus omega 1 equals to omega 3 minus omega 2 and so on. Whereas in logarithmic scale, it follows a geometric progression. Geometric progression means omega 2 upon omega 1 is equal to omega 3 upon omega 2. Okay, so this is unlocked. So what happens? What is the advantage that we get over here? You can represent really small frequencies. You would not have been able to represent if you were representing 1, 2, 3, 4. Where would you would have never got 0.01 and 0.1. Whereas it is important to expand the low frequency components, because you have a time constant of the system, and if the time constant of the system is large, means the system is going to achieve the steady state condition at some later point of time, or a good time lapse is there before it achieves the steady state value. Then you'll see that you'll have some very important behaviors in lower frequency regions. Like you'll have corner frequency there only, because corner frequency is 1 upon t. We'll see that now also. So if this is large, this would be small. So we need to see, okay, where my system is going to show some change in behavior from, let's say, a constant magnitude to some other magnitude that is having some constant slope. So for all those reasons we need to like have low frequency region can be expanded thing is the advantage here. We also get a larger range of omega because it is geometric progression. So you go on multiplying by 10 when you're talking in decades. That's why. So both of these reasons motivate us to go for logarithmic scale. Okay. Now, if you are given, just a second. Okay, if you're given a, a transfer function and it is represented by p1 of j omega into p2 of j omega upon p3 of j omega, if you're supposed to write it in logarithmic scale, you can see that it can very well be expressed as a combination of various logarithmics. Okay, so obviously anything that is in the denominator multiplied in the denominator, when it is converted to log, it can be represented as plus. If it is in the denominator, you can have a minus sign before that. When we talk about the phase, it is phase of p1 j omega plus phase of p2 j omega minus phase of p3 j omega, because phase is ultimately tan of tan inverse of the things that you have in the denominator and the numerator. All right. Okay, so this phase plot also varies with omega, and omega here is again in logarithmic scale. Now the basic building blocks of any transfer function that you might have seen until now are like this only, that you have some constant value, you have some integrating term, you have some derivative term, you have some somewhat complex integrating term, somewhat complex this derivative term, and if you have a second order system and the reciprocal of that. These are the standard forms only which we have seen till now. If you go for some other order systems, it can definitely be any higher order can be definitely be expressed as combination of second order systems. But these are the basic building blocks. Okay, so we should really anytime you can like derive it also, but we should always be in practice that what would they look like if we are asked that they should be expressed in there, or we need to draw their Bode plots. Okay, so for constant functions, so I hope you might have gone through the lecture, so I would not go in detail. But if you have a constant term, it would forever be constant 20 log of k, right? Because k is the constant here. GS is k. 20 log of k is the constant that you're going to have throughout. For phase, it would be 0 or 180-degree depending on what is the sign of k. It is greater than 0 or less than 0. Important concept here is this decade concept. So decade is 10 times. So if we have omega and then 10 omega, that 10 omega is said to be 1 decade above omega. Point 0.1 and omega, point 0.1 omega and omega means 10 times is the difference. So 0.1 omega is 1 decade below omega. Okay. Now that decade is uh, like uh, in terms of 10 only we define it. Now we are going to see what dBs per decade we are going to decade or like accelerate. So we'll see that. First of all, equivalent to this decade, we have a concept of octave. So we'll have a question today also, where octave is like omega to omega, 0.5 omega omega, a factor of 2. So it is 1 octave above omega, 1 octave below omega. Okay. If you have an integrating term, your magnitude is minus 20 log 10 omega, right? Because you have 1 upon j omega, then you take the magnitude, it is 1 upon omega, and then you bring it to the numerator, then you get a minus sign outside. So that is it. So this is your magnitude. For phase, it would be minus 90 degree. 1 upon j is in the denominator, right? So it is minus 90 degree. So if you are told to plot this, the magnitude thing, how would it look? So this is, I'll explain only for this one. So let's say we need to check at omega. Okay, at omega. So at omega, you'll get this thing only. All right. At omega, what will you have? Magnitude would be equal to minus 20 log 10 omega dB, right? Now, if you're asked to check at 10 omega, what would happen? At 10 omega, it would be minus 20 log 10 omega, right? If you try to break it, what you would get? Minus 20. So you can take them. I hope this is very clear that how this thing is done. I'll write it here. Minus 20 log 10 10 minus 20 log 10 omega. Log A into B is log A plus log B. That's why. So you see at omega, at omega, it was minus 20 log 10 omega. Whereas at 10 omega, it is minus 20 minus 20 log 10 omega. So you see, as we went from omega to 10 omega, the uh, slope that we fell by is minus 20 dB per decade, right? See, this is an increase in decade, but our magnitude fell off by minus 20, fell off by 20 actually. So we observe minus 20 dB per decade. So you can see here at omega, if it was a 0, at 10 omega, it is at minus 20. You can check the magnitudes from here. What would happen if omega is 10? If omega is 10, this would become 0. Sorry, I did some mistake. Yeah, yeah, yeah. If omega is, we already did for 10 omega, no? Yeah. If omega is 10, we got this and it is decaying by minus 20. Okay. So at 1 we had this value, we have minus 20 times, minus 20 less value at 10 omega. All right. Now, similarly, if we go with this GS is equal to S, you will see similar thing and you will see that it rises at a slope of 20 dB per decade. Okay. If you are allowed, okay. If the cases of, so a general first order transfer function is represented by this equation. Okay. If you have 1 upon Ts plus 1, how would it look like? If you convert it into the magnitude form, it would be of this form and angle would be of this form. Now, we need to see because it might exhibit multiple behaviors due to the presence of omega term and it is somehow related to time constant. So we want to check what would happen at low frequency, what would happen at high frequency. So this is basically an approximation that we make because it is really difficult to plot for every omega. So it is easier if we can make some approximation. When you try to do omega is less than 1 by t, you see that it is a 0 dB magnitude throughout. As soon as you reach omega to be greater than 1 by t, it decays at this slope. So this is high frequency asymptote, this is low frequency asymptote. All right. So, and moreover, so this frequency is important. This frequency is called corner frequency. And this corner frequency is represented by 1 upon t. So you will see for this 1 upon ts plus 1, you get the slope. All right. You have a corner frequency over here. And then you have this decaying at minus 20 dB per decade. Same as what you had in 1 upon s. So it exhibits similar behavior to that of 1 upon s. And this is the additional part. Okay. Now, similarly, you can draw the phase plot. For ts plus 1, it would exhibit opposite behavior. You'll get it rising plus 20 dB per decade. Now, this is very similar to the behavior of S. Okay. Another thing is, if you are given a transfer function of second order, omega n upon s square plus 2 zeta omega n plus omega n, how would you find the Bode plot and everything? So if you're supposed to do so, there is a low frequency asymptote, there is a high frequency asymptote similarly, because here you have the that time in the last question or last this integrated and differentiated term, omega was compared with t, time constant. Here omega will be compared with omega n. So we'll have to see for low frequency, for high frequency. When we see that, we ultimately find out is, what we ultimately find out is omega is equal to omega n is the corner frequency. All right. Okay, now we'll proceed with the questions. The questions will be based on these concepts only for today. We'll have complex questions in the next class. But yeah, in the y-axis of the magnitude plot of the Bode plot, y-axis means the magnitude part. The magnitude of sinusoidal transfer function pj omega is expressed as. So we read that we represented g of, sorry, p is given here, p of j omega magnitude is 20 log of pj omega is base 10, right? So your answer is this. Then, which one of the following is not correct about using a logarithmic scale for a plotting frequency in Bode plot? Which is not correct, okay? A large range of frequency can be represented. We saw earlier that we can represent a large range of frequency because it follows the geometric progression. So we can very easily move from one decade to another. So this is definitely correct one. The lower frequency ranges can be expanded. Yes, we saw that. We can represent 0.01, 0.1, then 1, then 10. So this is also correct. Okay. If we, I'll check the last option first. If point C, this is A, this is B. If point C is exactly halfway between A and B, the value of frequency at point C is the geometric mean of the corresponding values at point A and B. So we saw if you have omega here, omega 2 here, omega 3 here, then omega 2 upon omega 1 is omega 3 upon omega 2. We saw already. Okay, so this option is also correct. So another thing is zero frequency can be represented. Now we should check this really. So if we are plotting, let's say we are taking the magnitude. So 20 log 10 of g j omega. And we want to check at zero frequency. So this term becoming zero, what would happen? Log is not defined. So when we take the frequencies, it starts from 0.01 0.1 omega, 1 omega, 10 omega, and so on. So we don't take 0, not allowed. So this is the correct option. This is incorrect here. Okay. Now moving to the third question. Okay. If a plant transfer function is expressed as this, means PS is written as Fs upon Gs, then the magnitude in dB of the plant transfer function is what? What would be the magnitude? If you're supposed to, it would be 20 log of log 10 of Fs upon Gs magnitude, right? dB. How can you write this? 20 log 10 Fs minus 20 log of Gs, right? It's this option. All right. So the basic principles how log operates. It's the same thing. Okay. In the same problem, if PS is Fs upon Gs, PS is Fs upon Gs, then the phase of the plant sinusoidal transfer function is, what is the phase? In phase, we do not have any log. Log in phase, no. Okay. So it is just angle of f of j omega minus angle of g of j omega. All right. I hope it is clear. These are very easy, simple questions. Okay. Consider PS is 10. Let's say our plant transfer function is 10. Then the magnitude in dB and phase of the corresponding sinusoidal functions are what? So my PS is 10. If I want to find out what is the magnitude, what I'll write? G of, sorry, why do I write G? P of j omega is 20 log P of the 20 log of log 10 dB. So it is 20. Why 20? Because this is 1. So it is 20. So my magnitude in dB is 20 dB. Now I am asked what would be the phase. So what is PS here? It is 10 plus J0, right? So the angle of P of J omega can be given by tan inverse of 0 upon 10, which is 0. Right? So answer is 20 and 0. I hope this makes sense. Okay. Then the slope of the magnitude plot in dB per octave of 1 upon j omega is 1 upon j omega is same as 1 by s, right? So we saw we should know how to solve this. It's not that we should remember yeah, it should be in this way only. That is fine. It comes with practice. But still, we should know if we want to find out what is the slope actually, and if I'm not going wrong, I'm not thinking it to be rising as my plus 20 per decade. We should be very well clear with the concepts. Okay. So, okay. So I'll solve this question for you. G of j omega is 1 upon j omega. So G of j omega magnitude is 1 upon omega, right? Now I want to have magnitude in dB. It would be 20 log 10 g of j omega magnitude 1 upon omega dB. That means minus 20 log 10 omega, right? Now I want to plot this. This is, okay, let me take it to be 0.1, take it to be 1, take it to be 10. You can take any three frequencies. It's not a problem. Okay, now let's check the value. This is my magnitude. What would happen at omega is equal to 0.1? Magnitude would be what? Minus 20 log 10.1. Means it would be plus 20, right? So let's say this is my plus 20. So I'll have a point here. Now let's see the second thing. At omega equal to 1, my magnitude will be minus 20 log 10 1, which is 0.
Madam,
Yes.
madam, there minus 20 log omega, no, madam.
Hmm. Where?
Omega is equal to 2 omega, madam.
Okay, you want to say, yeah, in octave, yeah, definitely. So what
Yes, ma'am.
I want to tell you that this minus 20 dB per decade is equivalent to minus 6 dB per octave. So usually what you will see everywhere in all the examples that you will be dealing with decades only. If you are well versed with this decade thing, you will be able to answer in octave also. So
Yes, ma'am.
I'm solving it in decade form and both are equivalent. So we saw this here, no? Mm, yeah. So we instead of going for omega and 10 omega, we can check for omega and 2 omega. So there also will get, but the calculation is not that I mean helpful not I that is not that easy. It's a bit time taking because you have everything on scale of 10. So it's always easy to work with decades than octaves. That's why. So this relation is very important. It will help you. Okay. Now at yeah, here we got 0. At omega is equal to 10. Magnitude would be minus log 10 10. It would be minus 20. So it would be here. So you will see this. It's going at minus 20 dB per decade, which is equal to minus 6 dB per octave. All right. So this is the correct answer. Okay. Okay. Now we will have another transfer function and we want to find out what is the corner frequency here. Okay. So you can compare it with what is the first order transfer function? Right? So T here is 2 when you compare. And how is corner frequency defined for a first order system? We already saw that omega, right here, corner frequency omega is equal to 1 upon T. So your corner frequency is 1 upon 2, which is 0.5. It is equal to omega n when we deal with second order systems, but for first order system, it is one inverse of time constant. So this is your answer. Okay. Now Okay. The magnitude in dB of the sinusoidal transfer function corresponding to problem 7 as frequency tends to 0 is what? So your transfer function is 1 upon 2s plus 1. When we write it in magnitude, or let me directly write it, 1 upon 2j omega plus 1. Okay. As frequency tends to 0, what happens with the magnitude? That is what we want to find out. Okay. So we'll find what is the magnitude first. It is minus 20 log, or for simplification, I'll write it in this way first. Minus 20 log 1 upon under root of 4 omega square plus 1, right? It can be written as minus 20 log under root 4 omega square plus 1. It can be written in this form. All right. Now we want to say what happens as frequency tends to 0. So we want to find out limit omega tends to 0 magnitude of g of j omega. So we can write limit omega tends to 0 minus 20 log, sorry, 10 is missing here, log 10 under root 4 omega square plus 1. What will get? Minus 20 log 10, 1, which is 0. So as frequency tends to 0, your magnitude is 0. Okay. I hope this makes sense. We'll move to the next question. I'll copy this. Okay. The phase corresponding to the problem 7 means this one at the corner frequency is what? So what was my corner frequency? What we had found out? It was 0.5, right? Yeah. So our corner frequency is 0.5. Okay. Now the phase at this frequency, that means what is the phase here? It would be, for numerator it would be 0 degree, right? For denominator it would be tan inverse of 2 omega, right? And as I would write here only limit as omega tends to 0, it would be minus of tan inverse of 0. Sorry. I have to find it out at 0.5. Omega is equal to 0.5. Then it would be 1, which is minus of 45 degree. All right. Okay. Okay. The corner frequency of this transfer function is what? So again, this can be compared to tau s plus 1, right? Where so if we try to compare it, how it would look like? Your PS is 2s plus 4. You'll have to take 4 common. Okay, so it would be 0.5s plus 1. Now if we try to write what is the magnitude, It is 4 into 0.5 j omega plus 1. Magnitude here is equal to 20 log 4 plus 20 log, sorry,
He asked only corner frequency, madam.
yeah. We'll need this actually in the next question probably. Yeah, I'll write it there only. From here you can find out what is the corner frequency, and corner frequency is 1 upon t, and 1 upon 0.5 is 2. Okay, then yeah, this is the transfer function that we'll be using again. The magnitude as frequency tends to 0. It is again a similar question. So let's check what would be the magnitude. 20 log. When we take the magnitude, it would be 0.5 square plus 1. So it would be 20 log 4, 0.5 omega. 20 log 4 plus 20 log under root 0.25 omega square plus 1. Now limit omega tends to 0, p of j omega is 20 log 4. Put the value of 0 over there, it would be 20. If I'm missing to write 10 as the base, please assume that there is a base. It would be 1. That means that this whole term would become 0, and you'll be only left with this term 20 log 10 4. It can also be written as 40 log 10 2. What is the value you're getting? Something in dB. Please solve and tell me.
$12 dB, madam.
Sorry?
$12 dB, madam.
Yeah, 12 dB. Okay. So it was a very similar question that we did earlier. Now, we want to find the phase corresponding to the corner frequency. Okay. So you had obtained a corner frequency of 0.5, right? So what we want to do is, let's find out, okay, g of j omega. Your transfer function was 2 into s plus 1, no? What it was? 2s plus 4, okay. 2s plus 4. So definitely, okay, I'll write it here again. So this is your transfer function. Now we want to find the phase. So this constant 4 does not contribute anything to phase, or does it? It basically gives you just 0, right? So what you'll have, 0 plus tan inverse of 0.5 omega upon 1. And we want to do everything for, just a second, what was the corner frequency? Have I written it correctly? It was 2. It was not 0.5. Okay, so the corner frequency was 2. So it is tan inverse of 1, which is 45 degree. So answer is 45 degrees. Okay, now, okay. So this is the time you have got the second order system for the first time. And the transfer function is given as follows. The magnitude of the low frequency asymptote of the corresponding sinusoidal transfer function is what? This is what we want to find out. So if it is said that we want to find out low frequency asymptote, that means what? We want to do everything for omega tends to 0. Okay. Now, so essentially we want to calculate the magnitude when omega tends to 0. That is the whole question. Okay. So your GS is given here. To be 1 upon s square plus 3s plus 9. Okay. So G of j omega is what? 1 upon minus omega square plus 3j omega plus 9, right? Now, when we try to find the magnitude, it is minus 20 log 10 of we want to find out the, so can anyone tell me what is the value that you'll get here?
9 minus omega square.
Minus omega square?
Yes, ma'am. 9 minus omega square.
9 minus, oh, okay, you're telling me in
Whole
this
square
way. Huh,
plus 9 omega square.
9 omega square. And can you tell me, so I was asking you
Omega
to
is equal
simplify
to
this.
omega is equal to 0, madam.
Okay, you want to
Then
put it here only. That also works. So it would be minus 20 log 10. So I'll have to
square root of
just a second. Omega is equal to 0. Okay. So it would just be 81, right?
yes, ma'am.
Yeah.
Minus 20 log 9.
Yeah. What is the value that you get?
Minus 19.1, madam. Directly.
Good. So the magnitude at as frequency tends to 0. I should not write it in this way. Actually, it should be written like this. Limit omega tends to 0. You get 19.1 dBs. So this is your answer. Okay. Now, in this problem, what is the corner frequency? So, our transfer function was 1 upon s square plus 3s plus 9. It can be compared with omega n square plus s square plus 2 zeta omega ns plus omega n square. We can compare this, and we know already from the notes also, you can see it was properly derived that the corner frequency in this case is omega n. Your natural frequency is actually the corner frequency for this case. So what do you get omega n to be here? Omega n square is equal to 9, right? So omega n is equal to 3. That's it. Your corner frequency omega is equal to omega n is equal to 3. All right. Okay. Okay. For the same problem, what is the resonant frequency? So for resonant frequency, what else do we need? We need zeta also, no? So from here, let's calculate zeta also. 2 zeta omega n is here is equal to 3. Your omega n was 3 already. That means zeta is equal to 0.5, right? Now, what is the formula for resonant frequency? Zeta is 0.5, omega n is 3. Let me write this. What is the formula for resonant frequency?
Omega n into square root of 1 minus 2 zeta square.
Yes, very good. This is your resonant frequency. 3 into under root of 1 minus 2 into 0.5 square. What is the answer? Something in radian per second.
2.12, madam.
Okay, very good. So 2.12 radian per second. This is the resonant frequency of the system. All right. There is another question which I want you to solve. This is the last question for today's session, and I want to know which of the options is correct. So there are basically two transfer functions that are given over here: s plus 2 upon s plus 1 and 2 minus s upon s plus 1. So which of the following is true? So what we actually want to find out, what is the high frequency magnitude value? What is the high frequency phase value for both of the systems 1 and 2? I mean, you have to find out the high frequency magnitude, high frequency phase for system 1 and 2, and any of the options of these would be correct. So please solve this. Uh, I would tell you what all values I will ask you, but you start solving on your own. So G1 is the first one. I want to know what is the magnitude. I want to know the phase. Please tell me all of these as soon as you're done. Uh, Once you're done with this, then I want to know I want the value, I mean, the expressions and values corresponding to these eight parameters. Did anyone get the answer? Got the answer? Please let me know if you're solving, else I'll give you the answers directly. Okay, I'll wait for 2 more minutes.
Fourth one, madam.
Fourth one. Okay. But how did you get it? Like, I want the values corresponding to all of these.
G1 of G of j omega is limit omega tends to infinity. That is 1 0, madam.
This one. Okay.
Next one is also 0.
Second one. G2 of j omega.
G2 of j omega. G1 of j omega is also 0 angle.
This is also 0. Okay. And the last one?
Last one is 90 degrees.
Is it 90 degree? Shouldn't it
90
be
or what?
minus 180 degree?
Minus 180.
Yeah, because you get. Okay, I'll write those values also.
Minus 180 plus 9 minus 90. For denominator also we get the angle.
Yeah, so from both of them you get minus 90 minus 90, right?
Minus
Yeah, so it adds up to 180. I'll write the answer here
no
also.
madam. Numerator minus 180. Denominator minus 90. Okay, minus 90 minus 90.
Yeah. So for G1 of j omega,
Omega by 1 madam.
yeah, and for this it should be 20. So this question is really related to one of the problems that we had solved when we were discussing about this RHP zeros. So minimum phase system, non-minimum phase system. Then we had made some derivation that what is the phase if the zero lies in right half of the S plane versus if it lies in the left half of the S plane. How the this uh, magnitude is not always equal to uh, 0 degree. It could have some other phase and it could be a minimum phase system and all of that. So this question is related to that only because you have two transfer function and you can see one of them. In one of them you get zeros in the right half, in one of them you get zeros in the left half of the S-plane when the denominators are the same, like the poles are both of them, for both of them the poles are always in the left half of the S-plane. So this question was related to that only, and with this the lecture had ended for your ninth week uh, regular session. I have written the answers here directly. More or less, it is conveying what is there, what how it is there from the question. But if you like to convert it into j omega and then like write it in 2 or 3 steps, it is good to do so, because if you're beginning with it, then it is you will not make any mistakes. So you can also use that way and come at this point. If you haven't solved right now in the class, please solve this and get all of these answers today itself. If you wish, take a snap of this page and solve this question. You should get the following answers, and hence this D option is correct. Okay, the high frequency phase value of the sinusoidal transfer function of system 2 tends to 0. Okay, so in the next class, we'll see more intense questions related to Bode plots, and we'll also see the Nyquist plot, Nyquist stability criterion. So, yeah, uh, thank you for joining the meeting. See you next time. Bye.